I think we can start, Alina.
Hello, Professor.
Hello again. Welcome back to our 12th chapters series of lectures on water management, the Israeli experience, chapter 7. My name is Yoram Morag. I am the Special Envoy for International Water Affairs at Mashav. As some of you already know, Israel, a semi-arid country, has managed in the last decade to solve its acute water problems. The secret lies in a holistic, integrative approach to the subject. A lot of challenges to confront, and none of them can be neglected. We already spoke about the important role of wash and water management in difficult times, relating, of course, to the corona crisis we are all confronting. Water management in agriculture, education regarding ways to reduce water consumption, water harvesting, and urban water loss reduction. The future lectures that will take place every Tuesday at 12 o'clock GMT, 3 o'clock Israel time, will discuss water quality control, water reclamation, desalination, national and urban water management, and last but not least, innovation and water tech. Today, we have the honor to host Professor Hadas Mamane, Head of Environmental Engineering Program, Faculty of Engineering, Tel-Aviv University. Professor Mamane will talk about disruptive and sustainable water technologies. But before giving her the floor, a few technicalities with your permission. 1, the lecture is recorded. It will be uploaded to the YouTube channel of Mashav MATC, as you can see in the background, in my background, and will be available there together with the recordings of our former lectures. It is also available now and later on Facebook Live. Look for the page of Mashav and MATC over there. Questions. Please write the questions down here on the chat options, addressed to everyone. Professor Mamane will answer them at the end of the lecture. The lectures are a joint venture of Mashav MATC, our training center, and this is a good time to thank Alina Doncic and Ora Rabin for the hard work they invest in this program. And Mashav, Israel's international aid agency. Please join us for about 100-second clip on Mashav. After that, I promise the lecture. Share, let's see if I can make it. Share screen. Choose the right one. V, share. And boom. Boom, almost boom. Boom.
Mashav, Israel's Agency for International Development Cooperation, was launched 60 years ago to share the know-how and technologies which provided the basis for Israel's own rapid development. Mashav aims to empower those living in poverty in a holistic and innovative way and support fellow nations and communities in their struggle to achieve sustainable development, placing people at the heart of its initiatives. Our agricultural programs use unique techniques and farming methods to increase sustainability, food security, and hunger eradication. We believe that investment in education is an investment in our future and an agent for change around the world. We coordinate Israel's official humanitarian assistance, building medical facilities and supplying medicine in the wake of earthquakes, floods, famine, and other disasters. Mashav promotes innovative entrepreneurship as a means of advancing growth and prosperity. We believe that gender equality and women's empowerment are central to reach sustainable development. Our philosophy is to leave no one behind. During 6 decades, Mashav has trained over 300,000 people from more than 140 countries and has established development projects worldwide. Mashav, Israel's Agency for International Development Cooperation, is celebrating 60 years of sharing its experience and partnering for a better world.
Okay, this video was produced 2 years ago when Mashav celebrated 60 years. So now we're much older, 62, but still young and fresh. Hadas, the floor is yours.
Thank you very much. So I'm really happy to be here and to see people from all around the world. So it's really exciting. And I would like to start with my presentation. I will just share it. Okay, so I would like to talk about disruptive and sustainable water technologies. And this is in light of the water crisis that we're facing today, and that it seems to become even worse with the years that are coming. So when I think about disruptive water, I actually read a book that was on the wonders of water. And actually this book said that there are hundreds of times more of water molecules in our body than the sum of all the other water molecules together. So what does it mean with how we perceive ourselves and what we are? And we may think of us as humans, but it definitely depends on the scale that we're looking at, because if we look at the number of cells in our body, we have more cells that relate to bacteria than human-based cells in our body. So this gives also another perspective of how do we look at ourselves. And so how is this related to water technologies? I would like to go through some path with you in order to discuss how all these things are actually related when we think about water innovation. So what is water? And I'm sure that if I will ask the audience here, or what is water, probably most of the people will say H2O, right? I think so. But I would like to show you something else very soon, and I will return back to the answer to this question. And water actually has endless dimensions. It's a beautiful thing. But when we think about the approach to sustainable water, what does it mean? Well, everyone is talking about getting out of the box. But again, what does it mean when we think about water technologies? What's getting out of the box? What does it mean? What is innovation in the water arena? What does that mean? Just assume that you can actually imagine and dive into the three-dimensional concept of water and feel, understand, and imagine what water is. Can that actually help us to understand how to develop better water technologies? How is a single molecule of water related to the millions of water molecules that we have when we drink a glass of water? How is it related to the concept of thinking of water? And so water interacts with each other through hydrogen bonds, and water is a universal solvent, and also water has many types of capabilities. So how do we harness these qualities in order to purify water? And this is actually a really big question, because when we talk about water innovation, what do we actually mean? What is our goal? So if we look about, everyone talks about the fourth industrial revolution, right? How do we relate to the fourth industrial revolution when we talk about water? So we should actually bypass the traditional thought processes, because the traditional thought processes actually does not allow us to supply water for everyone, okay? So we do have a gap there. There is a gap that actually we need to understand and solve. So, but if we look at accelerated innovation, which actually talks about innovation that is more efficient and is more accessible, how does that relate to poor water quality, and how does that impact the society and the environment? And can actually disruptive technologies leapfrog over the current risks that are associated with these technologies? So basically, can we take like new nanotechnology materials to clean water? Can we use artificial intelligence and big data to manage our water systems? What we can do with the fourth industrial revolution when we talk about water? These are actually questions that we need to look at. But there is a problem. Why? Because I'm a scientist, okay? I research in the lab, we do science, we publish papers, and we can invent many new materials and many new technologies that we think could be implemented. But if we look at reality, most of these technologies, they're not scalable, they're not affordable, and they're not relevant to point of use applications where they're mostly needed. So what does innovation mean? Well, when I think about innovation, I think that actually we need to talk about reactor design. So how do we take all these scientific concepts into a system? And this is where we have like a huge gap, okay? We have a really huge gap. And if I look at, I did recently my sabbatical in IIT Madras in India, and I just quoted something that Professor Pradeep said, that affordable clean water is a problem of advanced materials. But I would say that it's not just a problem of advanced materials, it's also a problem of all of these advanced ways of thinking, integrating them in a smart system, in a system that can actually work. So these are the gaps that we actually need to solve. Now, you remember that I asked you, what is water? And well, we're used to say that water is H2O, but if we look at all these drawings, so actually water is numerous H2O molecules that are bonded to each other through hydrogen bonding. Okay, and when we drink a glass of water, we don't drink H2O, we actually drink tons of H2O molecules that are bonded to each other, and water is the universal solvent. So all the different chemicals that pass through the water actually dissolve inside the water. Okay, so we know that all this happens, but how does it help us to purify water? Well, let's look at the human perspective. So when we think about humans, we can actually drink only a very limited quality of water. So most of the water types we cannot actually drink. So what does it mean when we think about water technologies? So what do I plan to talk about here? And it of course depends on the time and how we proceed. I want to talk about contaminants in water, and do we have a chance actually to really purify water? I want to talk about the impact of climate change on water quality. And I also want to talk about new technologies that are related to sewage treatment and data science, new materials and new light sources. So this is my plan for today. So I'll just move. So when we think about contaminants in water, well, when we drink a glass of water, and I'm showing you this glass of water again and again, but what do we actually have in this water? Well, water can be actually transparent, but it can actually possess like many things like arsenic and pesticides and nitrates and hormones and fluorides and pharmaceuticals and microbes and viruses and bacteria, protozoa, and the list doesn't end. So do we actually have a chance of purifying water in a way that can actually be good for us? And when we think about today, when they talk about how food needs to actually be healthy because there's a relationship between the food that we eat and the biomass in our body and how our body functions, well, I would argue that it's the same for water. So the water quality that we drink is actually very important. And what is the recipe, so-called, of the water that is actually good for our health? And is it that even the question? So let's look at about the limitations about humans. So look at this list, and this is a list from the WHO, the guidelines for drinking water quality. And when we look at these guidelines, we see like a huge list of chemicals. And of course, definitely we don't measure all these chemicals in our water because we don't have the capacity, we don't have the fundings to do that, we don't always have available analytical equipment. But look at this chemical. So do you see this chemical? It's called phthalate, and this is how it looks like. But this is only one out of an endless list of chemicals that are not supposed to be in water. And actually, the concentration is supposed to be 0. So where do we find this chemical? Well, we find them in open dumps. And actually what happens in open dumps and solid waste, even managed solid waste facilities, we actually have chemicals that leach out of the garbage, and they actually infiltrate to the groundwater. And we all know about plastics, right? So when we talk about plastics, most of us are actually worried about the plastics, the microplastics, the nanoplastics. But what about the hidden plastics, those dissolved plastics that actually dissolve from these bottles? Okay, so what about these? Actually, no one talks about it because there's actually not a solution to talk about all those chemicals that leach from those plastics into the water. And the technology to actually remove them is very expensive. So what happens with all these things that are really a major concern, and these chemicals are potential carcinogenic? So what happens with all this? And it's even not measured, but we know that the plastics that we use to drink in actually result in more of these chemicals in the water. So there's a huge process. And when we look at the technologies to actually treat those chemicals, then they're actually very expensive technologies. So we need to use, for example, advanced oxidation, ozonation, reverse osmosis, all these like big names in order to remove those chemicals from the water. So we are actually in a big problem, because I'm not talking only about the bacteria and the viruses, I'm also talking about the chemicals that are present in the water. And why do I say that we don't have a chance? Because what are the chances of actually removing all those contaminants from the water? So that's a big question mark. And I want to talk about now on a different aspect. And this is in light of the global climate change. When we talk about climate change, we talk about many things. We talk about water availability. We talk about the climate itself. We talk about biodiversity. But we don't talk so much about sewage and not about water quality. And I just want to show you a few things that we actually need to look at when we deal with water. So this is actually a report from the UN about climate change and water. Okay, so one of the things that actually I was very happy to read is that they emphasize the need to look also, when we talk about water management, to look also at sanitation. And that the policy also must include all these sectors. So water should include sanitation, and in all the discussions on water, sanitation must be there. So looking at the sewage, we cannot ignore that. So this is something that we really need to emphasize, and governmental mechanisms should really also look in that, and the impact of climate change on designing wastewater treatment plants and on looking at sanitation in general. So these are statistics that I'm sure, like many of you know, 3.6 billion people live in areas that are water stressed, and that we know that we'll have, like, the issues will just increase in 2050. And we know about that we're trying to limit actually the temperatures, limiting the global warming to 1.5% above the pre-industrial levels. But we're actually in a problem, because we think it will even reach like 2% in the Middle East, where I come from. So, I mean, if you look at here at the summers, it just becomes more hot, more dry. The rain periods become actually, we have like storms, we have less rain. So how do we manage water in light of these issues? And what do we need to do to be more water resilient in light of the changes that are happening currently in the world? And so I actually want to emphasize the issue of quality. So throughout this lecture, I will talk mostly about water quality, and not because of water availability, because actually water availability is something that we notice. So we notice the storms, we notice the floods, we notice all these things, and this relates to water availability. But my argument is that when we have less water, the quality is actually worse. So how do we deal with water quality when we know that humans are actually can drink a really narrow water quality that is healthy for us? So what happens in light of all these issues? And so definitely climate change will have an impact on our water quality. And I just want to look a bit about wastewater treatment plant design. So we know that greenhouse gases actually are emitted during the treatment of wastewater, and these relate to carbon dioxide, methane, nitrous oxide, and all these have a global warming potential. So all these gases, and actually if we look at about the global warming potential of carbon dioxide, methane, and nitrous oxide, the ratio is 1 to 28 to 2 to 65. And CO2 is actually emitted from aerobic respiration, and N2O is actually a source of gases that are released during nitrification and denitrification. So all these things are actually happening during a wastewater treatment plant. So we have release of all these gases. And we really need to look at that and look at the impact of the release of those gases with relation to the global climate change. So this is the case in the Hudson River in the US, that actually what they found is that when they have actually access of sewage and the sewage reaches the Hudson River, then they actually have far more greenhouse gases, CO2, emitted from the river. So this is like one thing to think about. And if we look at if we look at different things, then when we use wastewater to irrigate crops, then we actually increase the surface area that the wastewater is actually with contact with the atmosphere. And when we have this issue, we also have a case of release of gases to the environment. And so these things are things that we must look at. So we cannot neglect all the impact of the sewage on water quality, but also on release of greenhouse gases. And so these contaminations are very much happening all around the world. And actually, the sad statistics is that less than 90% of, well, almost 90% of the sewage is actually not treated. So it's discharged to the environment and with a huge surface area and results in release of those greenhouse gases to the environment. And in addition to that, there's also the issue of greenhouse gases in manholes. So basically, methane rises to the top because it's the less dense out of all the gases that released from sewage. And then carbon monoxide, so we have methane, then we have carbon monoxide, and then we have hydrogen sulfide. So we have all these gases being layered in sewage manholes, and then they can result in what happens with methane, that, for example, it actually, because it's denser than air, it displaces air. And so when methane is being breathed, it will result in actually human death. And when we look at raw sewage, so this is a housing area, and this is raw sewage mixed with water. Again, the gases that are released here are actually really potent gases that are released and are a result of sewage that is not being collected, not being treated, and released to the environment. So we do need to think about these things. So when we talk about water, water is never only water. Water is also sewage, and we definitely need to talk about these things and look at them when we talk about water management. It's supposed to be always water and sewage management. So I want to just show you like a small example on how actually wastewater treatment plants can actually result in better management of their sewage. So for example, if we look at a standard activated sewage treatment plant, it actually consumes energy, okay? So the energy that is consumed in a sewage treatment plant is about 3.2 kilojoules per every gram of COD, which COD is the chemical oxygen demand, and this is actually a parameter that relates to the organics in the sewage, okay? So potentially sewage has the chemicals, the organic compounds in the sewage have potential energy that can actually be used to harness and to treat the sewage instead of using fossil fuels. So this is actually a way to reduce the consumption of the release of CO2 and other gases to the environment. And just by looking, for example, at I'll just really talk about this like really shortly, just to emphasize my point. So even if you're not like a sewage engineer, so this is a standard sewage treatment plant. And we can see here that we have 26% and 70% of the chemical oxygen demand in generation of the biogas, of the methane. So actually, we can get actually energy by generating biogas from the sewage, okay? But if we improve our sewage treatment plant by adding, for example, and this is only like a very simple case where we're adding an alternative design, and we're actually adding a coagulant that results in increased percent of chemical oxygen demand into the biogas formation, then we actually result in more biogas formation, and that is actually helping to provide the energy source for treatment of the wastewater treatment plant. This is an example of another example for an anaerobic membrane bioreactor to treat sewage. So for example, in this case, we're only removing the organics, but we're keeping the nutrients in the sewage treatment. So the nutrients can actually be used to reduce the amount of fertilizers that we need when we irrigate with this treated sewage for the agriculture irrigation. So there are many ways where we can combine cross technologies and actually look at the big picture on how technologies can actually be used in order to reduce the amount of chemicals used, reduce the amount of energy used, and reduce the amount of fuel that is used in order to treat the sewage. So this is one way of looking at sewage. In addition, we need to look at diversity. So do we actually need to treat all the water to a certain level? But it depends actually on the application. And this is also another thing that we need to look at. So we do need to match our thought and think, combine the people that treat the sewage to the people that use the sewage for agriculture irrigation. Do we really need to remove the nutrients from the sewage? Do we really need to remove all the organics? Do we really need to generate biogas? And if we generate the biogas, how can it be used back to reduce the fuel consumption on treatment of sewage? Then also we need to look at the industrial wastewater. So industrial wastewater can also be a resource if we think a bit of it. So we have in the industrial wastewater all those like tons of contaminants. So what can we do in order to close the cycles, in order to have like an affordable technology that will actually be more sustainable? Okay, and also I would like to talk about another thing about the impact of climate change on emerging diseases. So actually 25% of the diseases is related to human related are actually caused by environmental changes. So climate change actually can drive, or climate change can actually give rise to these disease-causing agents to thrive. So this is also an issue that also we must think about. I would like now to move towards water, because I talked about sewage. I would like to talk a little bit about water. And I would actually like to emphasize the issue of water quality. So we all know about the changes in the climate change, and how this impacts floods all around the world. And so definitely when we have issues of floods, okay, this also impacts the water quality. So for example, when we have flood, we have mixture of different water qualities. We can have, for example, you can see this water that actually looks like chai. It's brown water, which resulted in anaerobic conditions that resulted in increased metal dissolution to the water. So these things actually happen in light of climate change. So the climate change does not only impact the availability of the water, but also about the water quality. And we really must look at that, and not only the water, but also about the sewage. So we need to look at this water availability, water quality, and sewage. We need to look at all of these things and not separate them, because the separation is actually not real. So we're also doing a lot of work in India on trying to predict water quality. And the idea here is actually to develop affordable and low-cost sensors that can actually be used to get more data, because data is actually our way to understand what's happening with the water. And if we actually go to those companies that develop the sensors and ask them, can you develop lower cost sensors that actually can be affordable? Why does a turbidity sensor have to be so expensive? And why can't these sensors actually can be developed in a lower cost? And I spoke to a few professors from electrical engineering that said, actually, there's no reason. There is no reason for having all these like high costs for all those sensors. Maybe we don't need this accuracy. Maybe we can lower the accuracy, but get a way to have affordable sensors in order to understand, because one of the ways to make a change is actually to measure. Before we measure, we cannot know what's happening, because we want to understand if we have sewage contamination, if we have microbial contamination, if we have heavy metals in our water. We actually need to know what is the problem in order to treat it. But unless we have an affordable way to measure our water issues, our water quality parameters, then we cannot actually understand what's happening to the water. So a big research topic today is actually trying to overcome those expensive sensors and actually to develop low-cost sensors that could be affordable, that we can use in various communities and actually empower the people and allow the people in the community itself to measure their water quality so they can understand by themselves if a technology is working or not, and that can really empower the people. And so this is an important research task that we definitely can tackle in order to understand how to improve water quality. And so when we're thinking about the monsoon and the changes and the patterns of the rain, we really need to understand that the past thought was that in dry places, they will become drier. In wet places, they will become more wet. But actually, the sad story is that in many places, the dry places became more drier and the wet places also became more drier. So this is actually, how are we treating our water quality in light of all these changes? So as I told you, I lived in Chennai for some time and it suffered like Cape Town from day zero, which meant that there was no more water to drink. And this is something that is very sad because I cannot perceive the feeling of how it is to not have water to drink. And when we talk about not having water to drink, what about the quality of that water? And this is something that we're not even talking about, because we're talking about supplying the water, but what about the quality of that water that we're supplying? So my argument is, again, when we have less water, the quality is even getting worse. And the problem of brackish water. So overpumping results in brackish water. In Israel, for example, we're a semi-arid country. We do suffer from brackish groundwater, which actually results in impact on the food production and on desertification. So these issues actually must be tackled because the amount of soluble salts does increase. And humans cannot drink water that has a high concentration of salt. So it's easy to dissolve salt into water. It's more difficult to separate salt from water. So it's not an issue, but we can definitely do it, but it's expensive. So these technologies are actually expensive. So I want to return back to dynamics of water innovation. So when we talk about water innovation, what are we actually talking about? Are we actually talking about high-tech technologies? Are we actually talking about central water treatment technologies? Are we talking about point-of-use technologies? Are we talking about reactor design? Are we talking about maybe giving the basics of having a few liters of water to drink? What are we talking about? And I would also want to talk to companies, to the business people, because I feel that they are not, I mean, maybe it's both ways, but if the scientists, together with the business people, together with the NGOs, okay, we can together actually talk together, and by using the different thought processes, actually improve the water quality and its quantity as well. But we do need to find a common language. We do need to talk to each other. So in most of the cases, scientists and universities, they publish papers, that's it. People that work with the business, they want to know what is their next gain. And maybe investing in a scientist is not an immediate gain, I agree. And the NGOs, they should also, so if we manage to find systems where we can actually combine, talk to each other, that would be the best thing to do in order to solve our pressing and burning water issues. And in addition to that, we need to actually develop technologies in water tech that are based on renewables. So we cannot power our water technologies from fossil fuels. And if we do that, then we're actually increasing the problem. So we need to think, how can we use biomass? How can we use solar sun to power our technologies? And that's when we need to talk together with all the different disciplines in order to solve that problem. We need to, in some cases, look at natural biological systems actually to solve many problems. So it's not always about intense treatment technologies. We can actually work on improving, and this is, for example, a project that we're working on, improving sewage ponds by using simple supports where microbes grow on these supports. And that way we have a combination of algae and microbes. And we saw that actually the CO2 removal of these sewage plants was actually much better. So we can do these things. We can actually think of affordable ways to improve water quality. And definitely we need to look at the circular concept. Okay, so we cannot isolate water, we cannot isolate sewage, we cannot isolate climate change. We need to look at all the different things together and see how one process is actually benefits the other, okay? And I just have a few more minutes, 5 minutes, which I would like to talk about a little bit more about my research in my lab. One of the things that we're actually developing is disinfection technologies using LEDs. So we all know about light emitting diodes, which are actually used everywhere, and actually it's very common. But these LEDs can actually be in different wavelengths. They can be in the violet wavelengths, and what we found is that when we combine different lights from different wavelengths, okay, actually they can improve the disinfection ability. So we see here, just for E. coli, for example, just by combining different wavelengths. Okay, this is just by doing this. Okay, I'm not saying anything else, just by combining different wavelengths, we have more than 99% efficient inactivation of E. coli, and also we check that on sewage effluent. So when I'm talking about thinking differently, we can actually combine things. We can actually do things to improve our treatment technology. And with this technology, we're actually now working on developing an off-the-grid disinfection technology that is based on LEDs that does not require electricity at all and does not require chemicals. So it's chemical-free, electricity-free, off-the-grid LED technology based on solar, on the sun. So this is like one of the goals that we hope to develop. Another thing that we're working in the lab is also developing aerogels. So aerogels are really cool materials that they're actually 99% air. So it's only 1% mass and all the rest is just air. And that's why they're used as an insulator. So these materials are really cool, really nice. And, but if we look about these materials this way, they're expensive. Okay, it's expensive to make them. So how can we actually use these aerogels and prepare them from actually affordable materials, okay? and also prepare them from different biomasses that are present in the environment, and also encase them in a reactor that can actually be used for point of use small systems. So this is, for example, like questions that we're trying to solve. This is an example of how aerogels can actually absorb dyes, and then we collect the dye in the sponge, and then we can actually purify the water in a really simple way. It can also relate to other types of dyes. So this is, for example, using an earth-abundant catalyst in order to solve textile dyes. We're also trying to look at smart sewage pits. So we know that a sewage pit is actually a pit that collects the sewage. But what if we make our sewage pit are also our treatment technology? So we're now trying to, for example, to develop aerogels that can absorb ammonia, okay? And that way, we can layer with different aerogels with different types of qualities in order to actually prevent contamination of toxic gases that are vented through the sewage pit, and also absorb contaminants that will result in decrease of those contaminants to the groundwater, okay? In addition to that, this is the last thing that I want to talk about, is that I want to talk about data and data science. So how can data science actually improve the operation of wastewater treatment plant? This is a project that we're doing together with Mekorot, the Israeli water company. And so we have a huge number of parameters that are collected. But how do we use trends, numbers, and all these things in order to understand how can we improve the treatment of sewage? So we want to actually find anomalies. We want to predict. We want to know ahead of time when we're going to have a process upset. Because what happens today, we have a fire and we're turning down the fire. So we're actually, this is what we're doing. We see a problem and then we try to solve it. What happens if due to this enormous amount of data, we can predict the problems, or we can reduce the amount of data that is being collected? So that's when we combine with experts that deal with data science, with artificial intelligence, in order to develop algorithms that will really help us make smarter decisions on our treatment of a sewage treatment plant. So for example, we're working on 2 case studies. One of them is that looking at microscopic observations of the activated sludge sewage treatment plant in order to understand, can this microscopic observation alert on bad effluent quality? And the idea is to predict, okay, before we have the bad effluent quality. So then the idea is actually to look at all this data, and by using data science to understand, look back at all the data when we had good effluent quality and when we had bad effluent quality, and then trying to predict, not by human prediction, by machine. And in addition to that, another example that we're trying to look at process anomalies is alert before we have clogging. So clogging can result from sanitary wipes, but it can result also from debris clogging. So both of these can actually clog a sewage treatment plant. And we're trying to understand the correlation between the type of clogging and to have a possibility to actually predict. And so these tools can actually benefit humanity and for smart sewage plant control. And with that, I would like to end, and I hope that I was not talking too fast. I do have the tendency of speaking really fast, and I hope my students, when I teach them, that they do not suffer. I really want to say many things in a relatively short time, so I hope it was clear. I know that I enjoyed, I'm almost used to talking by Zoom, but I do look at your faces during the talk. So thank you very much. Thank you.
Wow, thank you very much, Hadas. I found it fascinating. I started thinking of maybe I should go and learn at the Faculty of Engineering. Maybe you'll be my lecturer. You are talking fast, but then we have the privilege of watching you over and over and over again, because as I said, um, it was also broadcasted on Facebook Live, and it will stay there forever as a post, and on our YouTube channel from tomorrow on. There are quite a few questions, I must say. Are you ready for that? Good. This one comes from Chennai. Maybe it's a place which is familiar for you. And it says the following: Chennai Metro Water is planning to recycle all its sewage with IITM technology. The recycled water will be let into water bodies to stabilize and then use for human consumption. Your comments on this idea, please.
Okay, so first I just want to say about something about Chennai. Chennai is my home. So for me, having a question from someone that came from Chennai is like very exciting. And I just last summer, I was there for 3 months. And actually last February, before all this Corona crisis, I also was in Chennai in IIT Madras, where I did my sabbatical. So I think that in light of the fact that there's overpumping and that the groundwater quality has decreased to, in some cases, the total dissolved solids reached even 2,500 milligrams per liter. These are water that human cannot drink. So we really need to look at what is the alternative. We cannot use reverse osmosis for every use. And so we know that reverse osmosis treatment plants, they also have an impact on using fossil fuels, CO2 emissions, and also it's very expensive water. So we really need to look at diversifying, using different types of water sources. And I believe that, that they will do things in a way where it will be actually, the water that will be generated through recycling will be affordable, and that it will actually provide a solution to the lack of drinking water. So I'm very much for this concept or way of thinking. And I know that it's very difficult to accept these things. It's not easy. But do we have another alternative? I don't think so. But definitely we need to strive to have a synergy of technologies and to improve the quality in a way that will be the best that it can, provided the amount of efforts and money that could be put into the technology. So definitely different minds need to come together to think of how to do it in the best way.
Okay, actually the next question also deals with water purification, and it's quite intriguing from my point of view because it's talking about something I didn't know that exists. Purification of water is being done by using filters made up of heavy metals. Is that way of purification will give us the pure form of water? To what extent is the water being purified? What kind of impure water can be purified using filters made up of heavy metals? Are those filters only used for purifying industrial waste? Interesting.
Interesting. So
you know, heavy metals, I didn't know that it's being used. It's new to me.
Please, the person that sent this in the chat, this question, I would be happy if you contact me personally, because I would be very interested to know on which filters I'm talking about. I'm less aware of using heavy metals as a filter because a metal is an ion. Maybe, I mean, maybe it's like some type of magnetic bead or I'm sorry, I'm not really sure what they're referring to, and I would be very happy if that person would send me an email because I'm very interested. Maybe it's a new technology that I'm not aware of, so I'm very happy to learn new things. But my apologies, I'm not aware of this type of filter.
Okay, so maybe I'm not too lousy with my knowledge regarding water purification.
No, but definitely I'll be happy if that person sends me an email. I'm interested to know what he's talking about.
Yeah, with pleasure. Alina will send an email to everybody after the lecture so that you'll have an email address that you can react to. Okay, another question. Dear Hadas, what is your recommendation to learn more on circular and the economy related to water? Thanks and congrats.
Wow, that's an amazing question, because actually I can say that I started to look at circular economy just recently, just maybe in the past 2 years, because we were educated to look at things. So for example, to look at things as a unit operation. So if we look at a filter, we look what's, like as engineers, we look at what's happening inside the filter, what is exiting the filter, and only looking at that unit. But that's actually not the right way to look at things. And only recently I started to think, I mean, because I read also other scientists doing that we really need to look at the entire cycle. And it's not just words. We do need to look at the entire cycle, because otherwise we cannot develop a sustainable technology. We cannot treat water and not look at sewage. We cannot do this and not do this. We really need to put all the pieces of the puzzle together. And if I don't have the capacity to do that, I need to join power with someone else that does have, and we need to like develop, we need to talk together. We need to talk together, but be very practical with solutions. But we definitely need to look at circular economy. So for example, so if we're looking at solid waste, we need to look also at the contamination of the ground. We need to look at which materials can we use for different resources. We need to look, for example, with algae, can we harness the algae for bioenergy? So can we, for example, use the oxygen that the algae release to the water, maybe to generate ozone that can disinfect? So we need to look at all these complexities. And it's difficult for one person to look at a cycle, because our mind is not operating this way. I mean, maybe only like if we have like a disruptive mind, but still we need to talk together. That's the main point. But also I just want to just say one thing, that the universities do not always like support like big collaborative projects. Especially when publishing like papers and all that stuff. But I think that these things are actually changing, that we understand that our power is when we think together. So yes, definitely we need to look at all the cycles. And even when I showed you about like anaerobic processes in a sewage treatment plant where they use methanol, so only afterwards they start to understand it's a fuel-based material. So they start to understand the CO2 that is emitted due to the use of an organic compound that is inserted to a sewage treatment plant. So we definitely need to look at all these aspects. We need to involve people that deal with life cycle analysis. We need to involve people that deal with technology. We need to involve people that deal with human-centered ways of thinking, psychology, all these things. And this is what we're trying to implement like in our project in India and South India and Kerala, which makes it so exciting because we come from so many disciplines, but not only universities, but also NGOs and all. And for me, it's an amazing school. So yeah, we do need to look at all these. I'm sorry, I spoke too much. We do need to look at all these. Yes, thank you.
You're okay. Okay, two short questions regarding UV LED, which is interesting for me because I'm more and more interested in water management that regards offline communities. So the first question asks about UV LED and smart sewage pit. Is it feasible for small communities? And then the other one is asking, can LED technology be used to treat groundwater for domestic use? So in the sense that they're very close.
Okay, I believe the question is yes for both of these answers. So we, as in the university, we do have the capacity to take the time and research things and understand. But at the end, we need to make things practical, because currently the cost of LEDs, UV-based LEDs, are very expensive. So they cannot be used in communities that are poor or things like that. I mean, it's really efficient, but it's expensive. And also, if we combine with aerogels, which are really smart materials that we showed that they can absorb textile dyes, they can absorb like different contaminants from the water, they're also very expensive. So they cannot be used as is. The technology is not ripened yet to be used as is, but however, there's like a big issue that we can actually improve things. So one of the things that we did in our research, and this is like a collaborative project, we wanted to see, can we use lower cost LEDs together with the expensive ones and get the same inactivation. And we worked also on viruses. By the way, we also worked on the human coronavirus, which is a paper that we're now publishing now. So what we found is, yes, we can do that. We can actually combine something that is cheaper, something that is more expensive, to get a synergy. So we can do these things, but if we look at the prices of LEDs, they reduce dramatically all the time. So even if today they cannot be used as off-the-grid disinfection technology, I believe that in a few years from now, we will be able to use these technologies. But they can also be used for groundwater, but but I think it's less relevant for groundwater. It's more relevant for disinfection. But the new materials, they can actually be used for absorbing contaminants in groundwater. So it really depends on the combination of technologies, but it's not ripened yet. It's not ripened yet for industrial use, but. And this is like what we're doing. The Israeli Innovation Authority, for example, we submitted a proposal together with a company to make these things more commercial. And this is the way that the industry helps the scientists, because we don't have the capacity to make things like affordable or to make them a technology. But when we combine with companies, it makes it like more easier. So that's where I discussed before that it's possible, but we need to work together. Otherwise, it will not happen.
Wow. Actually, it's not my word. It's the first word of the next question, which is the last one. And actually, I think that we'll need another hour in order to relate to the question. Fortunately enough, I think that next week, when Sarah El-Hanani, who's with us also today, will give her lecture about water quality, maybe she will relate to that because she has lots of experience in treating lakes. And the question is coming from Guatemala. I'll read it as a whole because in a sense, I think the same thing regarding your lecture. Wow, thanks a lot, Professor Hadas and Mashal.
Thank you.
My question is, what would be the most important thing to do to clean our lakes and rivers? Shalom from Guatemala. God bless. So, Sarah, show me a sign if you're going to relate to that question next week. Sarah, can you hear me? Wave if it's okay. No. Wait a second. Okay, now we can hear you.
I have to prepare my presentation first and to decide. Okay, I can.
Okay, we shall see. So, in a sense, I think that we can conclude this lecture. I enjoyed it very much, I must say. I hope that you all did. Reminding you again that if Hadas spoke too fast for you, you can go back to the lecture and hear it again on YouTube or Facebook. And I really hope to see you also next week, because as you can see, things relate to each other. And in a sense, in order to really get the whole picture about the way that, at least here in Israel, we treat water management, one lecture is not enough. So hope to see you next week, and have a wonderful week until then. And take care. Thank you.
Thank you very much.
Thank you.